There's a few people trying to get coffee.
Okay. Useful, okay.
Yeah, sorry, I maybe.
Stay away from me. How do I go? Here. From you. Not really, I'm scared. How much fun you have. Okay, it's my pleasure to welcome you to the morning session this Wednesday. Our first speaker will be Boris Doubrov, who will continue his lectures about Cartan geometry via exterior calculus.
Thank you. So, we'll skip the slide we had last time, but with a quick recap. So, last time we spoke about how Cartan connections can be defined on the base manifold, and then what is the allowed transformations, and these are gauge transformations we've seen already in other talks. And I started speaking about projective connections, and in particular, we discussed what is the development of curves and how development of curves looks like, in particular in projective geometry. And it turns out that we can write very explicitly the equation on those on projective geodesics. So these are the curves that develop into straight lines in projective, in flat projective space. And we ended up with very explicit expressions for these equations on projective geodesics. So just to illustrate that what we are speaking about is can be computed very efficiently. So now, what is the topic of today's talk? Is okay, yeah. So it turns out that this mapping from projective connections to geodesics is not one-to-one. So different projective connections may end up with the same geodesics, projective geodesics. So the question is whether or not we can find out a unique projective connection among this class of projective connections having the same geodesics, sharing the same geodesics. So this naturally leads us to a notion of normal projective connections, and again, I am still very much in scope of original Cartan's paper, and this is, I believe, very first time where the notion normal projective connection as well as normal conformal connection was introduced. So, and we keep on calling such connections normal today. What do we need for, what does this really mean, and what we need to define this one-to-one correspondence between certain classes of curves or differential equations and connections. So the key ingredient in the definition of normal projective connections, and in general in putting some restrictions on connections we consider is a curvature tensor. We've seen this curvature tensor already appearing, so I'm glad that I don't need to speak much about the objects which were introduced in other talks already. So curvature of Cartan connection is essentially defined like that. It enjoys important properties, so it's still right equivariant. It is actually vanishing on all vertical vectors, so it's very easy to define it on the base manifold itself as an object on the base manifold. And we also have a structure equation here, which is a generalization of Bianchi identities for Levi-Civita connection, for example. And most importantly, curvature measures the difference, how far our Cartan connection is from the flat one or from the Cartan form of the Lie group. So omega is equal to 0 if and only if it's 1-to-1 should be. So so omega is equal to 0 only if and only if the connection is flat, which is the same as locally equivalent to Cartan form in G. And we can impose some other conditions on omega, and one very natural one is called torsion-free connections. And again, we know this term from probably affine connections and the torsion of affine connections. So this is actually a very general term in scope of Cartan connections. We say that a Cartan connection is torsion-free if its curvature takes values only in a subalgebra G0. And in general, omega modulus this subalgebra is what's called torsion. Just to repeat what I was saying, so different projective connections may have same projective geodesics, and we'd like to ensure we can choose a unique one, and the choice should be natural. So what we'll do as an exercise in case of projective connections, we'll first show that we can always find a torsion-free projective connection with the same geodesics, and then we need to find out what are the other conditions, and we'll impose conditions as linear conditions on the curvature. So it's not differential equations; it's only linear algebra, and we'll try to find further restrictions of the curvatures that would guarantee the uniqueness of omega. And
may I?
Yeah.
So, what is the sense of difference? So, for example, if you take an automorphism which preserves the geodesics, take the pullback, is it a different one or the same one?
The pullback of a form on the base manifold
Of the connection form.
Yeah. So, well, I'm not sure I fully understand the question. So we have a class of projective connections sharing the same geodesics. So if you have a transformation that maps, that transforms this class, it certainly maps this family of geodesics to another family of geodesics. And if we are able to find a unique connection in this class, and this is what we'll do, and this is what's called normal projective connections, then we ensure that this equivalence now maps exactly this normal connection to the other corresponding normal connection for a different class. And this enables us so this gives us a one-to-one correspondence. So essentially it reduces the geometry of geodesics to geometry of normal projective connections.
And the geodesics are all unparameterized?
Yes, yeah. Here I speak about, well, actually development can be thought both in terms of parameterized curves and unparameterized curves. And actually, when I give equations for geodesics, I present them both in parameterized and unparameterized form. When I will be speaking today about sharing the same geodesics, projective geodesics, I will mean unparameterized geodesics.
I think maybe some confusion when you say normal connections. So you talk about two connections simultaneously, right? Class of linear connections and Cartan connection, right? So
I never speak about linear connections. I only speak about projective connections. So I stay in the scope of Cartan connections. So today, at least, so we speak only about, in my talk, about projective connections. I do not identify projective connection with equivalence class of linear, of affine connections. I'm not going to do that. It is possible, that's another language. It's another classical way to define projective connection as an equivalence class of torsion-free affine connections. And that is what is commonly used today, but that's not how Cartan did that. So he just spoke about projective connections without any mention of equivalence classes of affine connections. Projective connection is just Cartan connection with a model modeled by projective space. So that's important to say, but yes, well, there are different languages developed after Cartan, and they seem to use different approaches, equivalent, but I probably don't have time to discuss all possible ways to envision projective connections. I will go in detail or in the simplest example. So this would be projective connections on the plane. So it's a two-dimensional situation where the equation on geodesics is a single, on unparameterized geodesics is a single second order ODE with a cubic, with right-hand side cubic in first derivative. So I think we had it here. So that's the equation we have in case of n equal to 2. And we'll see how we can find a unique normal projective connection associated with this equation. So that's what we are going to do now. And we are doing this on, there are ways to speak about this in a very general way and in probably 2 lines. As we are in the training school, I'll do this very carefully and in a few slides, as in a few lines, just to give you a feeling how it really is done when you would want to compute something explicitly. So, as we discussed before, we can always choose a section so that our projective connection pulled back, or projective or form of Cartan connection pulled back to our two-dimensional manifold looks like this. And I denote x and y would be our local coordinates on the plane, on the two-dimensional manifold. So that's first thing to do. Now let's review how we compute. Let's find very explicitly the coefficients a, b, c, d in terms of a coefficient of this form. So I recall that if you take any curve on the plane, unparameterized one, we can, as we've chosen some coordinate system, we choose x as the local coordinate on this curve. So we really look at the curves as graphs of functions y of x. And we restrict our form to this curve. So this is what we get. That's one form. Now on the curve. As we discussed next, we would now try to modify this section again to kill this slot at the bottom left corner of this matrix to fix the direction, to normalize the direction of our curve. So to do that, we'll choose a section along the curve that looks like this. So we have this slot here, and if we now use the gauge transformation using this section, we'll see that it will exactly eliminate this slot, but make the next element here quite complicated. So we'll get, that's very explicit here. So we have this thing appearing, and actually a vanishing of this expression is exactly the equation on geodesics. So our equation on geodesics is written exactly like that. So you see that it depends only on omega ij's. So omega ij's appear here, only in this slot. So it does not depend on 2 other slots in the connection matrix that take values in T1, in G1, sorry. So this is the equation. So again, back to the question: how can we ensure that? So if you have some second-order ODE, which is cubic in y prime, and we can see that this one is. You see only y prime squared here, but if you evaluate one form on a curve, you get another y prime. So it's really a cubic expression. And very explicitly, so if we write now our forms, instead of using the classical gamma ijk notation, that would be classical, I especially use alpha betas to make sure that we look at this in a very explicit way. So these are our forms of a Cartan connection on the base manifold. So now we substitute them into the equation, and this is what we got. So this is very explicit way of writing the equation of projective geodesics. So terms, coefficients of this equation are linear combinations of the coefficients of this form. And you see, of course, that's, for example, here, we have, we do not see forms omega 01, omega 02 that are part of our projective connection. They don't show up in this equation. So equation does not depend on these forms. And also here we have 6 coefficients that define the freedom on the base of our projective connection, or G0 part of our projective connection, and only 4 linear combinations end up to be in the coefficients of the equation. So if you want to guarantee uniqueness, you have to impose 2 additional linear conditions on these 6 coefficients, plus we need to somehow find a way to extend these coefficients to the definition, these forms to the forms omega 01 and 02 in a unique way somehow. So this is a game we are going to play, and as I said, so the tool here is really to compute curvature and see how these coefficients show up in the curvature and impose the conditions of the curvature. So first one is we impose the conditions that we are torsion free. So it's omega, no, we have to see this, so omega 01 and 02 are here in our matrix. So you want them to be 0, and that will exactly mean that we are in a torsion-free case. Very explicitly we compute them, and it turns out that this gives us exactly these 2 missing linear conditions on the coefficients of forms omega ij. So with these 2 forms, whenever we have a cubic second order ODE, an arbitrary one, it uniquely defines us 4 forms. Omega ij, well, we already normalized in the curvature form the top left slot to 0, so omega 11 is equal to minus omega 22, and these are these expressions. Fairly simple. So that was to find this. We just needed to solve 6 linear equations. Simple linear algebra. And we ensure that for any such equation, we determine these forms and get this part of our projective connection. So again, we still have 2 forms missing, and we need to define them. So these forms that are in the G1 part of our Lie algebra, or top right corner, top right block, they're still arbitrary. So we would need to have more conditions on our curvature to guarantee the uniqueness of these 2 things. And it turns out that we can ensure that not only torsion vanishes, not only this part vanishes, but we can also guarantee that this part vanishes. That's a very strong condition, and this is very specific to case n equal to 2. I will speak about how it looks like in higher dimensions. But in case n equal to 2, we can actually reduce, we can choose forms omega 01 and 02 such that the only part of curvature that will survive, so automatically this will be 0 because we are in the cell 3 case, so only this slot will survive. Very small part of our curvature. And then, and this is again, we can write very explicitly what this means. We end up with 4 linear equations exactly on 4 coefficients of this form. And we can solve these linear equations very explicitly. And derivatives show up here because when we compute this slot, we need to differentiate, we need to compute d omega ij's, d small omega ij's, and the coefficients of omega ij's are these linear combinations of a, b, c, d, so first derivatives show up here. So that's, again, a very explicit parametric, explicit coordinate form of a projective connection on the plane that has a given set of projective geodesics. Well, as we just discussed before, this guarantees us that geometry of this second order ODE's cubic with respect to y prime is equivalent to the geometry of projective connections with these conditions on the curvature. And if a projective connection, and this is exactly what is called by Cartan normal projective connection, at least on the plane. So we say that a projective connection on the plane is normal if its curvature tensor has these conditions. So it's only non-zero part of the curvature stays in the upper right corner. So, and again, I don't know, so today, of course, normal projective connections, on the normal connections in general, there are generalizations of the notion of normal connection to a much larger class of connections. This is a standard object today. The motivation, I don't know what was the real motivation of Cartan, but at least I understood it this way. So that was the way to pick up a unique Cartan connection in a class of connections associated with the same class of projective geodesics, having the same projective geodesics. Well, if you go into dimension greater or equal to 3, this becomes slightly more complicated, and this already requires linear algebra. And I try to stay, at least in this talk, I'm still trying to stay as much as possible away from algebra. So I'll just briefly explain what happens here. Okay. So what happens? We can do similar calculations and show up that whenever we have a given system of ordinary differential equations defining projective geodesics, and this is again a special class of systems of second order ODEs. The right-hand side has a very special form, which I showed on some of the previous slides. It's a bit more complicated than just a cubic in first derivatives. There are certain quadratic expressions showing up there. Still, for a given class of projective geodesics, we can always find a torsion-free projective connection. And there will be many projective connections, torsion-free projective connections with an arbitrary or almost arbitrary choice of omega of top right slot here, omega 0 j here. And we would still need to find out some conditions of the curvature to guarantee that these forms are also determined uniquely. And now what happens, so we know if n is greater or equal to 3, we no longer can ensure that this part vanishes identically. That's just too strong. And the fact that it would imply that the connection is flat for n greater or equal to 3. So we write very explicitly what we have in the slot, in the middle slot of our curvature. We express curvature in terms of our connection form. So we get a tensor, which is here AIGKL. And we see that if we vary forms 0j here, we can ensure that this tensor is trace-free. Well, of course, it has some symmetry. Bianchi identity, well, structure equations of Cartan connection implies that this tensor is not arbitrary at all, so it has some linear relations. But this equation guarantees us that guarantees us a unique choice of omega ij. And that's exactly, again, we can, Cartan, again, this condition shows up in the original Cartan paper, and he does pick up this condition. It looks a bit arbitrary, but in fact, he clearly does a very clever work with tensors at this moment, and he does special calculation to ensure that this condition is actually invariant with respect to gauge transformations, because we have to guarantee, we have to check this, because we are working now in the coordinates on the base, so we have to ensure that any conditions we impose on our curvature would survive if we apply any gauge transformations. And that's what he is doing here, and that's again fairly simple linear algebra, but still it requires a bit of work here, which I skip here and refer either to original Eli Cartan's paper on projective connections or a number of other works, and in particular Chubb's Lovelock book on parabolic geometries, where all conditions on normality of for parabolic geometries are expressed very, very explicitly. Okay, so that was the case of projective geodesics and projective connections. And certainly there is some feeling of unsatisfaction here, because we were able to associate projective connections on the plane with a very special class of ordinary differential equations, second order ordinary differential equations, which are cubic with respect to y prime. So what if our equation is not cubic with respect to y prime? What if we have an arbitrary ODE of second order? What we can do, and what maybe some other ways to build a Cartan connection we can find. So that's exactly what we're trying to do now, and I'll show that if we now look at the arbitrary second order ODE, we can modify our model and model homogeneous space, and would still be able to associate a certain Cartan connection with a different model with this equation in a unique way, with the same strategy. So how does this work? First of all, well, a little bit of how one deals with differential equations. So for second order differential equations can be viewed, so we have coordinates x, y on the plane, so we assume that y is a function of x. Z, we introduce another coordinate z, which is just y prime. It's not written here, but z is y prime, and this is jet coordinates on first jets of maps from R to R. And then we have, we know that all solutions of this equation lifted to the first jet will be tangent to this vector field, or line. So dx plus z dy plus f dz, that's the direction. So essentially what we're doing here, we are rewriting second order ordinary differential equation as a system of two first order equations in a way. And then we would like to remember that we come from only xy coordinates, so we fix vertical direction of the projection of jet space, first jet space to the original coordinates xy. So this is another direction we would like to fix. And then it's a fairly elementary reasoning to say that two such equations are equivalent under change of coordinates x and y, arbitrary change of coordinates x and y, which is commonly called point transformations in the geometry of ODEs. So if and only if this pair of directions, these pairs of directions are equivalent. So we can associate to having another second order ODE, we can have another pair of directions. And actually, two second order ODEs are equivalent if and only can be brought one to another via just change of coordinates, if and only if you can establish equivalence of these pairs of directions. And I should probably have a geometric picture here. So these directions are two lines, E and B, and together they actually form a vector distribution, and it's very easy to see that this vector distribution will be spanned by vector fields dx plus zdy and dz. And this is exactly contact distribution, one of the models for contact distribution in RC. So this, at each point, we'll have planes which form contact distribution, and inside this plane we'll have two directions. So this is a geometric way to understand an arbitrary second-order ODE, and we'll now try to find another Cartan connection that is uniquely associated to this one. And first we need to define what would be the model of our connection. And
can I just ask a question?
True.
When you say the pairs are equivalent, what do you mean by the pairs are equivalent?
yeah, so this is a geometric structure on a three-dimensional manifold.
The plane could be the same, for instance. Is that what you mean?
Pardon?
The plane they span could be the same. Is that what you mean by the pairs are equivalent, or you mean?
Yeah. The planes may be the same, but so planes do not depend on the choice of function f. So for another equation, we'll have even v will be the same, but e will depend on the function f. So e is here, and for the other equation, we'll have e or whatever g, for example, here. And we say that they are equivalent if there exists a transformation that preserves contact planes and the vertical distribution but maps EF to EG, for example. Or more generally, we can well, that's sufficient.
And then this kind of equivalence then is...
Then it's guaranteed that this kind of transformation that preserves contact planes, preserves vertical distribution, is necessarily a lift of change of local diffeomorphism on the plane to the first jet. And then the conditions that it maps EF to EG exactly means that it maps one second-order ODE to another second-order ODE. So it's just encoding ordinary differential equations as geometric structures, in a way. Yeah. So now we need to find a model, and of course I have a model on the next line of my slide, but there is an easy trick how one can find a model. So whenever we consider a class of geometric objects, we can guess what would be the most symmetric one. Sometimes it's not obvious at all, but in this case, I guess we all understand that the most symmetric equation would be a trivial one, because we don't have a restriction on the right-hand side, so it would be the equation y2 prime is equal to 0. And then we know that our connection, projective connection, becomes flat when curvature vanishes, and it becomes, in this case, our connection form becomes just a Marot-Cartan form on the Lie group. So you can imagine that if you take our simplest object, then its symmetry group will be exactly as a group that governs the flat model. So if you take equation y2 prime is equal to 0 and try to find out symmetry, so what are the transformations that preserve this equation, there are many ways how one can do this. One naive way is to just do it very geometrically. So what is y2 prime is equal to 0? It defines as all straight lines on the plane, well, with the exception of vertical ones. But well, there are ways to include vertical ones as well with some easy geometric reasoning. But anyway, so these are trivial equation y2 prime is equal to 0 defines as straight lines on the plane. So what would be any symmetries of our equation would preserve a class of lines on the plane. So the transformations would be exactly projective transformations, because this is the most general transformations of the planes that map lines to lines. So it's the same group, the same projective transformations of the plane, with one trick. So now we are dealing with a three-dimensional space, so we associated certain geometric structure on R3, not on R2, with our equation. So what we need to do, we need to lift our projective transformations to the first jet. And this will be our model, actually. So the model will be the same projective transformations of the plane, but now lifted to the first jet. And again, there is also a very geometric way to understand what does it mean lifted to the first jet, because what is the first jet is a direction on the plane, and direction on the plane is uniquely associated with a line. So we point to direction at the point. So we can think about first jets as flags, points and lines or directions through these points. So that's how we come up with this model. So model will be full flags in R3 viewed up to PSL3, all linear transformations. And by all flags, I mean all, of course, lines and two-dimensional spaces on R3, which after, if you projectivize things, we get points and directions through these points. So the game we are going to play now, we would want to have a different projective connection, or different connection with a different model. I shouldn't call it projective connection any longer, because it will be a connection modeled by this homogeneous space. And to give you an idea, well, that's how we see algebraically the thing. So our Lie algebra G will be just traceless 3x3 matrices. What is a stabilizer of a flag? Well, we can assume that's just upper triangular matrices. That's what I denote by PST. So it's projectivized upper triangular matrices inside a PSL. And we have also a very natural grading here. So diagonal has degree zeros, and elements up under diagonal would be -1, and the next, the lowest left corner will be -2. I didn't have it here written, but I think that's also quite obvious. Here. So the grading is given like this: elements have degree 0, this 1, and this will be 2, and here it will be -1 and -2. So this is how we turn SL3 into a graded Lie algebra. And we would want to have a connection associated with this pair of directions. And again, there would be the same game we would like to play. So first of all, our connection should reflect the underlying structure. So this should be somehow aligned with these two directions. And second, we'll see there will be many connections of this kind, and among these connections we need to find a unique one by implying the conditions on curvature. So that's how it goes. So if you have any connection now modeled on this flag variety, for any such connection, we can actually define two one-dimensional distributions using an arbitrary section. So we take a section, we pull down connection form on R3 now, or on three-dimensional manifold. So and now we have, I should have it also in front. So we have 1, 0, 2, 0, and 2, 1. These are most important forms for the moment, which lie in the complement to G0. And we remember why these forms are important, because under gauge transformations, they transform linearly. So the other second term in the gauge transformation that involves Cartan form doesn't hit these three terms. And it's very easy to see that whenever we use gauge transformations would always preserve these forms and these forms. So these forms will be transformed linearly under gauge transformations. So therefore, if you take direction defined by this as an annihilator of these two forms, it does not depend on the choice of gauge transformation. So it's well-defined object on the base manifold. And again, I repeat again and again that whenever we define some objects on our base manifold using some section, we have to ensure that it doesn't depend on the section, which means that if you apply gauge transformation, that will be the same object. It's as if you are doing some linear algebra and ensuring that what we do does not depend on the choice of coordinates. So with what we want now to have, we'd like to have our connection associated with a given second order ODE, which means that we'd like to make sure, okay, that's, we would like to have that E is exactly the distribution, the line direction, the direction we have. E and V are the directions defined for a given second order ODE. And yeah, that's probably the explanation I just had, why the slots are transformed linearly. And so this second term does not affect omega 1, 0, 2, 0, 1, 1, 2. And these two forms are, these two spaces are preserved under gauge transformations. So E and V are preserved. So, yeah, to say it again, so we'd like to have Cartan connections on a three-dimensional manifold, which are naturally associated with second order ODE, which means that those E and V defined by these forms and these forms are exactly the ones we have given by second order ODE. Now, we'd like to find some normality conditions on the curvature. That's what we're going to do. And this is the result. What you I still have normalization conditions for cubic second order ODEs. So these were the normalization conditions we had to impose on the curvature to ensure there is a unique one. So in this case, the conditions are slightly different. They're still quite strong, so we ensure that there is no torsion. Torsion would sit in these three slots. We also ensure that there is no G0 part. There will be still G1 and G2 parts in our curvature, but they should look like that. Again, well, as usual, the natural question is whether this is gauge invariant or not, whether this is something that would be the same in all for all sections. And yes, it is. Again, that's a simple exercise in linear algebra to check that. And we are still in the examples where you don't need any more advanced techniques to check such things. So in general, normality conditions would require much more algebra for in other cases. But in these cases, these are like almost the only examples where you can have everything explicit. So very briefly, I have like 6 minutes now. So very briefly, how do we prove this thing? And not surprisingly, that's done by a very, very direct calculation here. And again, as an excuse, I again refer to Elie Cartan, who did it before. And in the paper of Elie Cartan, it's 2 pages, so it's not something terribly difficult to compute explicitly. In my case, it will be 2 slides, where I hide, of course, all the calculations, just guide you through how it looks like approximately. So as a starting point, we choose S. So we have the conditions that omega 1, 0, omega 2, 0 should vanish in a certain direction. Omega 2, 0 to 1 should vanish in another direction. Then we choose S, try to normalize G0 part of S, and then we are able to have to bring our three forms to this form. The only unknown function is k, but now we can be, so this determines s up to, takes values in G1, yes. So now you compute omega to 0, so you look at the top left slot, top right, bottom left slot, sorry, bottom, so this one, in your curvature, you'd like it to be 0, and this immediately gives you conditions from k is 1, and you have another condition that some other part of your connection starts to shape up. You go on, you impose two other conditions, omega 1, 0, and 2, 1, and then you get more and more conditions, very explicit. At each step you solve linear equations, nothing more. And these linear equations start to define all other components of your Cartan connection. And you remember that we still have a freedom of choosing a section. And at that moment, we can actually kill some of the coefficients by an appropriate choice of sections the same way. So it's a game we play. We have linear conditions, but we also view everything up to gauge transformations, and we use gauge transformations to normalize some of the coefficients. So that's what we get in particular if we assume that we are torsion-free case. Still a lot of freedom, still a lot of unknown functions here, and we need to go next to see what's going on. So when we assume that our omega is like that, so it takes values only in G1, then these are the formulae again. Well, I think I recalculated them myself, but that should be identical also. So this is exactly how they show up in Elie Cartan's paper. So I'm sorry for this terrible notation maybe sometimes, but that's how it looks like. So you, at that moment, when you impose these conditions, your forms, your connection form becomes almost uniquely determined, and this is the only function that is left unknown. And I use here another, so I use operator d by dx, that operator total derivative defined here. So the last step, we have to ensure that these slots are also not arbitrary, but have very specific form. And this determines our coefficient mu uniquely. So we end up exactly at the curvature we would want to have. That's the curvature, and under the choice, our choice of section, all components of curvature are uniquely determined. Moreover, now that's a nice thing. So you have 4 coefficients left in your curvature. They can be explicitly computed, so it's not a big deal to compute them very, very explicitly, and you recover some interesting expressions that did show up already in some other classical works, back to even 19th century works of, I think the very first person who did some systematic study of invariance of second-order ODEs was Tress, and this was, for example, a huge expression that was probably found first by Tress. I'm not sure if it showed up somewhere earlier. But you recover this one by this normalization of a Cartan connection. Plus another interesting invariant here, that's force derivative of f with respect to z, which is y prime. So you see that this thing has some invariant meaning, and we know this already, that the class of cubic ODEs, of second-order ODEs cubic with respect to y prime is somewhat special, because these are the ODEs that describe you projective geodesics, unparameterized projective geodesics for true projective connections on the plane. So, but why I show this here to you, that the whole calculation and even the explicit expressions of invariance can be recovered by just hand calculation in a very limited time. Depends, of course, on your skills, but you don't really require any computer software or anything else. and it is unlike like works of Tress where it takes him 50 pages to reach to this invariance. Here it's a few pages of calculations. Well, I think, yeah, I'll stop here because next will be what do you do with the curvature, with the structure function, well, with the curvature, and how do you derive more invariance, and how this machinery of invariant derivatives looks like. That was already covered by Jan Slovak in this particular case. So I stop here, and maybe I'll just briefly advertise. Yeah. So maybe as a very, very last slide, I just want to say that we are now, what I covered today was just the beginning of a long story, a long project that was aimed to associate normal Cartan connections to all kinds of ODEs or systems of ODEs. And so it started from Cartan actually, and then the scalar third-order ODEs were treated by Chern in 1940. Then there was Bryant who treated first-order ODEs, and then systems of second-order ODEs. So there is like really a series of papers where each next person was treating next class of ODEs. Then there was a general setup done by me with Komarkov and Morimoto. And then scalar ODEs of order 5 I handled myself. Then there was a student of mine who helped, with whom we managed to cover all other cases of systems of ODEs. So and if you would want to see expressions, explicit calculations, further ideas, or references, I put here a single reference where you can recover everything else. Yeah, so I stop here.
Any questions?
Yep.
Is there an easy way to see that the model? So we were talking about the flag on R3.
Yeah.
Is there an easy way to see that the model that we had, which was a quotient of PSL and PSD, that really is the model that talks about that flag? It just the link wasn't obvious to me.
Yeah, well, I think I tried to make this link. Okay. So naive way was this is what I tried to present, was to consider the most symmetric object, which would be y2 primes equal to 0, and then look at the symmetries of this object, and that would be exactly projective transformations.
Sure.
But then you have to lift them to the first jet. Because the geometry is defined on the first jet, not on the base manifold itself, and this lift means that with each point we consider a direction through this point,
right.
And that's exactly going from just P2 to flags in RC.
Right. So I followed that. The question was how do you get the particular model or the particular quotient of algebras?
Particular quotient algebra.
So you associated it with a particular quotient. You had the upper triangular matrices, and then you also had PSL3, I think?
Yeah, well, stabilizer or
Okay.
fixed flag is exactly
Okay.
upper triangular matrices. That's how I...
Okay. It was that last one.
Yeah. Yeah.
Sometimes people are interested in restricted equivalence problem. For example, you would like to consider classes which include interesting equations like Penlever, for example,
Yep.
right? And one of the classes of this kind was considered already by Sophusly,
Yeah.
y double prime equal to f of x and y.
Yeah.
Yeah. Of course, it has its own invariant,
Yeah,
and
yeah.
people started by the classical theory of differential invariance.
Uh-huh.
This problem, right? So determining the equivalent group,
Yeah.
which preserves the class, and then finding
Yeah.
this differential invariance. So how would sound the Cartan approach to this?
Yeah. Probably. Well, of course, the key ingredient here was that we can equivalently define second-order ODEs via certain very clear geometric structure, which is a pair of directions on R3 with span contact distribution. Whether one can or cannot define other classes of ODEs via local geometric structures is another question. So in this particular case, I'm not sure. But one of the attempts that can be made is using the naive approach. And the naive approach would say, well, we would want to consider equations y2 prime equal to f of xy, so we have no y prime at all. So what is the first of all natural equivalence group for such class of equations? So this will be a certain pseudo group, certain transformations that preserves this class. It will be smaller than all transformations of x and y because all transformations would introduce first derivatives on the right hand side. So there will be a smaller class. There will be a pseudo group that preserves this class of equations. And then we have to choose a model for a potential Cartan connection. So again, let's go for a trivial equation in our class. That will be y2 prime equal to 0. And look for symmetries of this equation, but in a restricted class of allowed transformations, under a smaller pseudo group.
How do you encode this? I know how it's done in general theory. How would you encode in Cartan language the smaller pseudo group?
Well, I mean, you use this, well, first of all, I don't know what pseudo group will be, so
That's known, yeah.
yeah, of course, yeah. At that moment, you don't need to do anything. You just look for the symmetry of the simplest object in your category. So it will be y2 prime equal to 0 viewed up to this smaller pseudo group of transformations. And you will result in a certain symmetry algebra, which will be your candidate for G. And the stabilizer will be G0. And then you look for an arbitrary Cartan connection with this model and would want it to be aligned with this equation. What does it mean aligned? That's a big question. That's probably you ask for. I don't know the answer immediately, and there is no universal recipe. But normally you can make sure that, again, one of the ideas is to go through distinguished curves, for example. So in your Cartan, in any Cartan geometry, you have distinguished curves. So you just want to make sure that these distinguished curves match with distinguished curves you have here, which is solutions for this ODE.
No, but the general question is it actually Cartan geometry, right? With this class. Can you do like normalizations on us?
Well, what is a Cartan geometry? Cartan geometry is a Cartan connection. Whether or not you can associate a natural Cartan connection to any geometric object, that's, first of all, we know it's not true when there are no invariant, so there should be many things from setup. So there should be, for example, the geometric object has to be defined by certain G structure in a certain way. Well, whatever it means, maybe higher order jets, maybe weighted jets, etc. Second, you need to have invariant normalization conditions, which you not always have, as we've seen from the talk of Nick. So it's worth trying. That's a good question and a nice example to try. That's all I can say. There are approaches here, but whether they work or not, I don't know.
Yeah, so if I may still. So maybe a very naive question, but could you briefly comment on what happens or what fails when you go from J1RR to J1R2R, or if you take just some kind of PDs, maybe very well behaved in their nonlinearities or something like that? Does something survive from the method?
Yeah, that's again, we need to understand whether we stay using ODEs or at least finite type PDs, what's called complete PDs, where you're able to express all higher order derivatives through lower order derivatives. Or you speak about arbitrary PDs, underdetermined or determined PDs. But in case of overdetermined PDs, which can be like, what solution space of finite type, that should work. Essentially, this series of papers was about ODEs, but this particular one in the middle deals also with complete finite type systems of PDEs.
And maybe some classical example of a PDE to which you can construct the Cartan connection?
Yeah. That's you just a complete. So, for example, say U is a function of xy, And well, one of the works we did is, well, that's again nice, known result, but in particular we had work on just this class, where you have all second order derivatives expressed through lower order terms. So this is a system. This is what I call complete system of second order PDEs. For one function of two variables. So for this one you have
Explicitly. Yeah.
very explicit. Well, you may play without this equation. You also get a very nice theory, but with a different model. But because the only reason why you are still able to do that, because if you differentiate 2 times, then you also get a complete system of PDEs. So this is what I call finite. That's not my term. So it's common term when your solution space of a system of PDEs is finite dimensional. So essentially, that's certain Frobenius system behind this.
Okay, so let's thank the speaker again.